Welcome, welcome, welcome. So, as of our last little run through, um, what we ended up, what we ended up with was a model that worked, right? We come to our curriculum. Um, oh, this is the old one. Come to our curriculum. We can see we worked on updating the training weights yesterday, and we ended up coming out with a way to load the state dictionary. I believe this is dictionary, uh, which is going to contain the weights for the final connected layer of our ResNet 18 model. So now that we have that situated and we can actually train, right? So if we source, then activate as always, hop into our virtual environment, and then let's go over to our source directory. And if we were to hypothetically so this is creating the dictionary that has the weights. This optimizer.step is what actually goes back and changes the weights. Lost dot backwards. I actually don't know what this does. Let's go ahead and figure that out real quick. Um, does lost dot backward. Hope you guys are having a good start to your new year. So it computes the gradients. When you ran the forward pass, PyTorch quietly built a computation graph that records how the loss was computed from the model's parameters. Calling loss.backward, which we do right here, tells PyTorch, starting from this scalar loss, apply the chain rule backwards and compute the loss parameter for every trainable parameter. Okay. So it's going to every node essentially and running the loss parameter, loss over parameter for every trainable parameter. So what changes after loss.backwards happens for every parameter where p dot requires grad equals true, which is going to be only our .fc, our final connected layer. The gradient answer is if I nudge this parameter slightly upward, how does this loss change? Nothing else happens yet. This y returns a scalar. Tuition. Forward pass, what happens? Loss was how bad was it? Backward, who was responsible and how much? So it's trying to figure out exactly which layer is necessary or which node is necessary to be updated, and then the optimizer is who goes and actually updates it. Let's see if that explanation is in line with what's actually happening. So loss determines who uh, affects the gradient the most, then the optimizer updates the weight. Loss defines how wrong the prediction is. We understand that already. Then backpropagation determines how much each parameter contributed to that wrongness. The optimizer then updates the weights using those gradients. We understand. Oh, actually, first, let's crack open Paint real quick. And I'm gonna stick with Paint. I tried using that note-taking app, and it's just I don't know. It's not really what I'm looking for. Set this up real quick. Paint's nice, just being able to have I don't know. It's just simpler, easier, nicer. So we'll keep it for that reason. Um, so one thing, you know, at the beginning of all this, what I started with was we'll talk about just me for a second, right? The concept of learning itself is really intriguing to me, right? How do we learn? How do we process information? How do we handle things along those lines? So, I mean, it's why I'm here right now. It's why I'm doing this, right? It's why I've done everything I have done in my life, whether it's learning languages, instruments, cooking, physiological movements, biomechanical, whatever it is, right? Learning is the invariant to all of that. And by invariant, I mean, like I said, this series, I believe, 100 million times. The invariant is the thing that doesn't change, right? Your invariant will never change depending on what problem you're working with, right? So let's say um, you're trying to figure out how to squat better, right? You want to figure out how to squat, yada yada, rar, right? So you want to figure out how to squat better. The invariant to this is going to be a multitude of things, right? But one of the first things that you can easily say with any workout, right? The invariant, what is always going to be present is some type of base. What I mean by base is, well, your feet. Depending on your feet, this can determine so many different things about your workout, right? So the feet is where everything, for me, right? If I were to choose the invariant, this is where everything should start from. Now, for me, again, I say for me because that's extremely important. It's for me. Your base is where everything else builds up from. For someone else, though, they might not care about the base, right? They might care more so about the ROM, the range of motion. So, how do you squat? What what movement pattern do you have when you come up, when you go down? Do your knees go forward? Do you try to keep them straight? Whatever the case is, you now have your personal variant of range of motion. So now you say, okay, I'm going to have this one strict range of motion, and everything else becomes your X, Y, Z variables to those things, right? So your X variable to this, if your invariant is range of motion, it could be your bar position. Where's your bar on your back, right? Whatever, blah, blah, blah. It could be your foot position now, right? But you treat this as a variable, as in I could change it wider, narrower, whatever. But what's always going to stay the same? Your range of motion. So that to me is the starting point for learning. You first need to find some type of invariant and then move from there. Right? Now, why am I saying all this? This is just one concept of learning that has been extremely useful for me and literally everything I've done, right? And it's gotten to a point to where it's kind of innate. I don't think about it anymore. I just always look for that environment no matter what I'm doing and move from there. So I kind of got antsy, I guess you could say, and decided I would like to learn something else about learning how to learn proper ways. I came across this amazing video that I might leave in the comments about learning how to learn. And one thing this genius of a man went through is to have these three different pillars. Okay, sorry. Let me start here. Learning itself functions within two, I guess you could say manners. First, you have your encoding, and then you have your retrieval. Right? So, encoding is us coming here and saying, well, what's cross entropy loss? Right? It's me looking at cross entropy loss, learning about it, understanding it for myself, right? And then storing that inside of my brain. This in itself creates something called memories. If you think about your learning experience, you're essentially forcing memories to be created in relation to the data. After that, once those memories are created, you start practicing by using retrieval. And retrieval is essentially, I mean, you can think of a lot of different ways. It's me sitting here right now saying, well, what's the optimizer do? And thinking about, okay, the optimizer goes back in the layers and is changing the weights and dealing with certain knobs like your learning speed or things along those lines, right? And as I retrieve, I'm essentially re-encoding as well, which strengthens my understanding of the concept. Okay. So, what does all this have to do with anything? Well, there's a concept. Sorry. Encoding itself is the single most important thing to the entirety of learning. Retrieval is the easiest to get better at, to see results, but encoding itself is how you can see something one time and understand it like in the back of your hand. That's what encoding does for you. So the question is, well, what system do we have to practice encoding, right? How should we be encoding? And for me, not me, but what I came across that I've been testing out and has been working really well is functioning with encoding inside of three different pillars, right? And again, I'm still practicing this, I'm learning this, but I can see how strong it is and how great it is as we go through this. Um, so first, you want to find the mechanism, right? Is So the mechanism is, well, how does it work? What's it do? How do you make it work? Yada yada, right? So if we say we're talking about the optimizer, the mechanism would be, well, it goes back a layer, it goes back through all the layers actually, and it will update the weights based off of what we're found with the gradients through the lost dot backward stuff, right? So you have your mechanism, and that's normally where people stop. But let's also focus on the boundary, right? Well, what boundary would function with the optimizer to make it not work, right? How can the optimizer not be functional? Well, what if all the layers are frozen, right? If all the layers are frozen, how can the optimizer do its job? These are all frozen, these layers, looks like a Pop Tart, but this is a boundary to the optimizer. If everything is frozen, it can't do its job. And lastly, you look for contrast. Contrast being what is the closest neighbor to this that can confuse people, right? So to me, you could say, well, the loss function. What the loss function is like the cousin to the optimizer, right? You are dealing with the loss function first, which us cross entropy loss, we're using the CEL. Um, and it's understanding this at the same level as you're understanding the overarching puzzle to the optimizer, right? Would be the next step. So like if you don't really understand cross entropy loss fully, again, find the mechanism, find the boundary, find a contrast to it. And if the contrast to this happens to be the optimizer, so be it. Now you understand these two topics truly, right? And your understanding doesn't fall apart right when you come across a boundary or when there's something similar. Okay. So I say all of that to say that's what we're going to do from now on. I just wanted to give like a context on why we're going to change things up a bit. Uh, so let's come here and see it in action, right? So first, we want to figure out what exactly is loss that backward doing, right? So you get the loss number from loss equals criterion. Criterion is the neural network cross entropy loss function, and you're supplying the x values, the logits, right, for each picture, and then the y values, which are the truth labels for each picture as well. So after you calculate this, you get the loss, and then now we're using loss that backwards. Well, okay. So let's figure out what's the mechanism behind loss dot backwards. So it applies the chain rule, computes loss over the delta of the parameter, the delta between loss and parameter, the derivative, I believe, right? Let's not, I believe, right? That's not a good. What is it doing exactly? How does it compute the parameter? Right. Produces gradients in param.grad. Large gradient parameter had influence on the loss. Okay, I see. So the mech. Okay, okay. This is this is it right here. This is awesome. So the mechanism to loss dot backwards, just this function right here, is first you're applying the chain rule to compute the gradient, right? Again, we're looking for gradient descent. We're looking for where that ball settles in that valley. If you guys can remember, we have a graph here, like so. Call it like that, maybe. And this is bad. This is a bad graph. Not what I'm trying to do. All right, let's try this again. So we have a graph, right? Boom. And in our graph, let's say it starts through here, goes here, it's like that. We find the derivative of this function, and we find it to be something along the lines of this, right? We find this right here to kind of be the derivative of that black line. And after finding the derivative, well, we know that if the x, I'm sorry, is y is 0 on the derivative, the slope of this function is 0, which is where we want to be because this is considered learning, right? If we start here, we say, okay, well, where's the slope negative? Is the slope positive or negative? It's positive, so let's go back this way. And then we settle, say we come here, and we say, okay, was it negative or positive? It's negative, which is good. That's what we want. So then we keep going this way. And eventually we settle somewhere around here in the middle. So the loss dot backward is doing that gradient learning, gradient descent, dealing with the gradient descent, and applying, uh, essentially selecting if it's a large gradient, small gradient, zero gradient on what the parameter is. So if we are working on our, if we're working on this, right, this receiver here, and for some reason it's chosen a parameter of face mask type. Right? I'm trying to draw a face mask here. It's not face mask type. Let's just imagine this is a beautiful new age face mask, right? And it's saying it's saying this is a parameter. Well, all right, where we're at here. we're saying this is a parameter. Well, realistically, the parameter has no bounds and weights on, sorry, not weight like our layers, our convolution layer weights, but weight as in meaning. Doesn't necessarily have too much meaning between cornerbacks and receivers. So this is something that will probably have a small gradient to zero gradient. And the loss dot backwards is what's assigning that to this. Okay. So we now understand the mechanism. Well, what's a boundary? Right? What is a boundary to loss dot backwards? Why? What would make it not work? If so, let's look it up. To me, first, I'm thinking. I mean, obviously, if it's frozen, right, you're not going to go backwards. Um, if I would assume if somehow, some way it's unable, if you don't have loss, right? If you don't have your loss, you're not going to be able to calculate the gradient. That's a boundary. Um, or if you have poor loss, right? If your loss is incorrect somehow, that also is a boundary within it. So let's read this first. How does it compute the loss and perimeter? So we handle the chain rule, and then you get the loss. PyTorch builds a computational graph. W linear Z softmax plus loss equals the logits, right? The weighted inputs. How to compute the starts at the loss, which is whatever number sets LL equal 1, multiplies the incoming gradient by the node's local derivative. Okay. Accumulates the results into dot grad, and then that's what your loss dot, or sorry, your optimizer then use. So why does PyTorch need to store immediate values from the forward pass in order to compute gradients later? Huh. Intermediate values from the forward pass in order, because that's what gets used inside of computing the gradients later, right? I don't think that's so. You disable gradient tracking, also that, right? You detach the tensor, you convert it to Python NumPy too early, the loss isn't scalar, nothing in the graph requires grad. So you see now we're understanding the things that might make loss dot backwards not work. And then lastly, I would say the similarity, the contrast, right? If we have the mechanism, we have the contrast, and now we have, no, sorry, we have the mechanism, we have the boundary, and now we have the contrast, which to me is gradient, not gradient descent, but the optimizer, right? Loss dot backwards is going through and handling the gradients to each node, while optimizer then goes through, takes the results of the dot grad, and then he plays around with the weights due to that. So with that, we have a nice, thorough understanding of loss dot backwards now, and then we understand what optimizer dot step is doing. So boom, now we're here, and let's go ahead and run. Wait, no, no, no. First things first is I want to be able to, right? The reason we're here right now is for day 18, for day 19, tracking, training. I want to make sure it's working, right? So I know down here we already have kind of a example of making it work. But like I've said prior, my programming isn't that good. So this is a good opportunity to take the time to try to figure it out myself and see if I can get some type of scoreboard going to make sure that each epoch that we're running, all right, make sure each epoch that we're running is properly doing what it's supposed to. So first, things first. We have our logics and we have our predictions, right? And we start with a function. Here, let's first do this. We're not necessarily looking to learn. Um, X in range 1. We're not necessarily looking to learn as more so come with a score, right? So let's run this training.py. Okay. So here we are. And it gives me an array. So within this array, if it were to match, it would be the same, right? So what I'll do here is say total equals, or just say total equals 0 and correct equals 0. No, we need this outside of the loop, right? Total equals 0, correct equals 0. And then we run our loop, right? And then on the first iteration of the loop, after we append, right? What I want to do is say you append, and then if x, or sorry, if trues x is equal to prediction x, right? Did I spell this wrong? Predict, predict. I know I spelled it wrong. Oh, I see. All right. So you get if trues x equals prediction x, then we're gonna say correct plus equals 1. Else, and then we don't even need to say whole else and everything. We can just then say also total plus equals 1, right? So this is going to cycle through every one, every range. After it appends, it'll check to see if they're equal. If not, if it is, then it'll add correct plus 1. Then you add to the total plus 1. And then after this loop is done, you say, well, print total and print correct. Let's see what's up there. Okay, so you're 2 for 2. So then now you're saying score is equal to total correct. Or sorry, correct divided by total. And then now I want to print score. Makes sense to me. So you have a 0.5. So let me multiply it by 10, or is it 100? I'm gonna say 10. No, 100. Sorry. Okay. So if we were to say 5 iterations, you get a 60%. Okay. If we were to say 10 iterations, you get a 75%, 40%, right? So you get the total after each epoch, but I don't think that's necessarily what I'm wanting. What if, hypothetically, we could do it like this instead? So after you finish that, you still print this, but inside of the loop itself, so we can see it go and see it learn, right? So now we have this, and we keep, you know, scores aren't looking too good. Uh, and then out of our, oh, we're looking at the validation loader too. Let's head over to the training uh, data loader, and then let's look at a batch size of 5. Right? We got a batch size of 5, and yep, as expected, not looking good. Great. That being said, though, we go ahead, get rid of that, and we run this for 30 epochs. Uh, that didn't do anything. Which is did not train well. What if I load the model? Huh. Okay. Let's do 100. It is progressively getting better though. Progressively, very progressively. Oh no, I think okay. I think just I think doing it like this is messing me up. Let's let it run, and then let's get the final score at the end. All right. It runs. It runs. It runs. Yeah, 84.3. Right. So let's say we delete this, and then we run this again. Can't load. Uh, I prefer it when it is on screen. So you get 64% off rip, right? But then if you say, okay, I'm gonna load it and then train again, it should update this to a better starting point. So then you do it again, we should be above 82, in my opinion. 85. That being said, it keeps 91. Technically, it should still be higher, still be higher, still be higher, right? 88. Okay. High enough to be able to say it's high enough, it's learning, it's working, right? Now, okay, how do I really want this score to be? Right. I like this here because I like being able to see it on every run through because you can kind of see where it stays at, right? Um, you just watch it get better, you know. It's tough here because it's let's see what they did here. Right. Train law. I'm not looking at train accuracy. Correct divided by total. Correct plus equals prediction. It's equal to YB. Oh, if the prediction is equal to YB, that's on the item. Okay. So we're tracking the training data now. What I would like to do next, actually, what I would like to do is now that we're saying, okay, we're at 90 percentile for the training data loader, let's look at the validation data loader. Let's get the range to, what is it, 2, batch size of 2. And let's run, let's not, let's load, but we're not updating again. Let's see what scores we get. Okay. So it started off rough, and then I started learning on that data set, but it's not necessarily working off rip. So that's not good. Okay. 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 That to me screams we need more data. That to me screams we need more inputs onto this. So what we're gonna do is grab some more pictures. um, I'll be honest, I don't want to necessarily bore you guys with this. I mean, I'm literally gonna sit here and just download picture after picture after picture. So this is gonna be something I'm gonna do off cam, and I think I will come back with probably 50 of each, maybe 50 cornerbacks, 50 wide receivers. It's just finding the pictures is gonna be the most tedious. I wonder there might be a way to make some type of application somehow, some type of scraper that will allow me to crop to download and crop a slew of images throughout the. But you would need an AI first to be able to tell you it's a wide receiver or not, now wouldn't you? Okay, yeah. I'm gonna get to about 50 cornerbacks, 50 wide receivers, and then the validation data I'll get about 10 of each as well. Different, completely new. Try to make it all different, and then from there, I think we'll be okay to move forward and keep testing and keep trying new things out. Really short today, um, but like I said, I don't necessarily want to bore anybody with this. Um, but we got our tracking now. We have a way that we can at least get a score, make sure it's learning, make sure it's getting better without having to sit here and look one to one to one to one. It just saves us a lot of trouble. Um, outside of that, I don't really have anything else. I really hope y'all learned something today, and I'll see you on the next one. Let me train on or let's see. I want to see if we could see anything about the parameter tracking. See if we can find out what parameters are being found somehow, some way, and then also retrain on new set. Okay. Wonderful. All right. Hope you have a wonderful